Hello everybody, hopefully everyone is okay. As you know, we live difficult days because of Corona, so please stay at home and be happy. I will try to do my best to give you good engineering knowledge about our course. Today I will show you how to use homogeneous second order equations to find the critical buckling loads of steel structural members. Engineers such as structural engineers, mechanical engineers and aircraft engineers needs to design their structural members not to fail due to material failures, due to yielding or fracture, and also they should design their structural members not to fail due to what we call geometric failure, such as buckling. So if you have a very long and thin steel structural member, and you press on it, you give it a compressive force, this member may get buckled due to its thin or cylinderness. So today I will show you how to find this critical buckling load, because the engineers needs to calculate these loads and to take a factor of safety and to prevent this type of geometric instability failures. So let us start. Okay. So let us find this homogeneous equation that you can find the buckling critical load. If I have this column, cylinder, long steel column, and it has a pin and pin connection. The column has a length L, from here to here it is L, and also it has a cross-sectional area A and a modulus and a moment of inertia I, and also a modulus of elasticity for the material, usually is from steel. Okay? So under the effect of axial force, under the effect of P, you press on this by an axial force. So because it is a cylinder column, this at some load, it may get buckled in this shape. Okay? So if I say this is the x-axis and this is the y-axis, so this is y, the lateral deflection is a function of x. Okay? So we know from strength of materials, mechanical engineers or mechanical students know that the second derivative of the deflection is equal to minus the moment m divided by EI. So if you obtain the moment at any point here, you've got a section here, and you will obtain here the moment at the deformed shape. Of course, there is axial force here, P. This moment is equal to P times Y. This is a Y, P times Y. So you will have Y double prime is equal to minus the moment is P times Y divided by EI. Okay? So if you take this to the other side, I will have here Y double prime plus P over EI times Y is equal to 0. Okay? So this is a second order homogeneous differential equation. So engineers needs to solve this. This is a constant number. I will call this omega square. Okay? second order homogeneous differential equation with a constant coefficient. P, a critical load, is constant, modulus of elasticity is constant, and moment of inertia is a constant number. And I have two boundary conditions. The first one is at this point, when the x is equal to 0, the y is equal to 0, and at this point, when the x equal to L, y is equal to 0, and at this point, when x is equal to 0, y is equal to 0. So I have two initial or two boundary conditions. So this is a boundary value, we call this a boundary value problem. So how to solve this equation? From previous lecture, you just write the characteristic equation, lambda squared plus omega squared, this is a number, this is not is equal to 0. This is the characteristic equation that you need to solve. So from here, my lambda is equal, if you take this to the other side, will be plus or minus omega I. So I have here a complex roots, and there is no real part, I have only imaginary part here. So the solution is a kind of sine and cosine function, which is C1 sine omega x. In this case, it's function of x, function of the position. And the x is changed, the y is changing. Plus C2 cosine x. So this is the general solution for this problem. So I will rewrite the solution, general solution for this problem. It is C1 sine omega x plus C2 cosine omega x. I have two boundary conditions. When the x was equal to 0, my y is 0, and when the x was equal to L, my y also 0. So I will plug here by this one. So I will put for the first one, I will plug here y is 0 and x is 0, sine 1, C1 sine 0 plus C2 cosine 0. Sine 0 is 0, cosine 0 is 1, so you obtain here C2 is equal to 0. Okay? So my equation, because C2 is 0, my equation from the first condition, C2 is equal to 0. So my equation from this condition, so my equation will be y is equal to sine 1 sine omega x. So to find the second one, the second condition, I will plug by this condition. When the x was equal to L, my y was equal to 0. So from here I will put here 0 for the y, C1 sine omega L. So instead of x I put L. I want to find C1. From this equation, as you observed here, C1 cannot be 0 because if C1 is 0, there is no solution. So this sine omega L should equal to 0. So we will say sine omega L is equal to 0. So sine omega is equal to 0. This will give you that omega L is equal to pi times n. N is changing from 1, 2, 3, etc. Okay, so any multiple of pi will give you this 0. Right? So, if I got the square of this equation, omega square, L square, n square, pi square. Okay? And I give a definition that in the beginning of this lecture that omega square is equal to P divided by EI. Okay? So I will plug this in this equation here. So it will be P over EI. L square is equal to n square equal to pi square. Okay? So the critical buckling load, P, is equal to what? Is equal to, just multiply this by that, be N squared P squared divided by L squared multiplied by EI. For minimum value of P, this N can be 1, 2, 3, 4. So the minimum value of N is actually, and N is equal to 1, this is equal to 1. So the critical load that will cause the buckling is given by this relation. Okay, engineers usually likes to write this critical load in terms of stresses. So if I write this load in terms of stress, okay, so I will divide, so the critical stress that will cause the buckling is equal to the P critical divided by the cross-sectional area of the material, of the member. Okay, so I will give, this is the critical load, pi squared E I divided by A and L squared. Okay, now there is from mechanics of materials, mechanical engineers know that we have what we call radius of gyration. R is equal to the square root of the moment of inertia divided by the cross-sectional area. We call this moment of gyration, radius of gyration. So if you got the square of both sides, so the radius of gyration is equal, R squared is equal to I divided by A. Okay, so if I rewrite this equation here, I will just take this moment of inertia down and the area down. So I can write that the critical stress is equal to pi squared over times E divided by, this is L squared, and this is divided by I over A. Okay? So just you take this down here, so this can be up here and this is down and up. Okay? So the critical stress is equal to, this is R squared, so it is pi squared E divided by L times R all square. Okay, because it's R squared. Okay, so the critical load is equal to pi squared modulus of elasticity divided by L over R. We call this the length of the member divided by the radius of gyration. We call this cylinderness ratio. Okay, so if you draw this curve, if you draw this equation, this is the cylinderness ratio L over R, and this is the critical buckling stress. You will obtain such a curve like that. Okay? So as you see, if you know the length of the member and the cylinderness ratio, length and R, which is cylinderness ratio, you can enter to this curve and you obtain your critical stress value. Okay? Lastly, of course, if you reduce the cylinder, this will go to infinity. This goes to 0. But of course, material will got some limit here. This is the yield stress of the material. It cannot exceed that. So you are dealing with this part. Okay. So I show you today how to use second-order homogeneous differential equations to solve engineering problem like buckling stress. Thank you for watching, and please stay at home healthy and wealthy. Thank you.